Hello, and welcome back to our series on building a web server from scratch in C. We are getting very close to having an actually functional web server here, and I will be doing a demo of it in the future. It is not really at a point where I'm done with it or anywhere close to done with it. There are many ways to improve what we have here so far, but we're getting to a point where I can actually put a website up with this, and I want to do that so you guys can actually see how it works. So what we're doing today is defining this launch function. And this becomes a bit tricky, but if we get it right, then things should work pretty well on this server. So let's go ahead and define our launch sequence. I'm just going to copy and paste it. By the way, in a previous video, I mentioned that I wanted the launch sequence to take an HTTP server. So in the actual server object embedded in HTTP server, I removed a launch function from here. I figured that you don't necessarily want a launch function in every kind of server that you use. You probably do, but no one's ever going to implement just a server object. It doesn't do anything. They're always going to want to build something on top of it. It's sort of a class template or an interface, you could say, if you're thinking about this in C++ terms. You wouldn't actually want to implement a server object. You're always going to embed it in something else. So this launch sequence makes more sense if it takes the HTTP server. Anyway, this is going to consist primarily of an infinite loop, but before we enter that loop, we want to define a thread pool. Now I created this thread pool object in a previous video, so if you haven't seen that, you can watch it. It should be up there somewhere. But we're going to first define a thread pool. And we want this because the thread pool allows us to handle multiple clients simultaneously. If you think about a web server that does not have a thread pool or doesn't use multi-threading at all, every single client has to wait for the client before them to finish with the server before they can be handled by the server. Whereas with a thread pool, we can handle multiple clients simultaneously, and it doesn't matter how long one takes. Imagine if you had to wait for someone else to finish watching their YouTube video before you could watch yours. You would just never be able to watch one. So we need multi-threading in this. So we're just going to define a thread pool, and we'll just name it thread pool. And we're going to construct one with the constructor. And here we just need to pass in the number of threads that we want. Now, I'm just going to arbitrarily pass in 20. In the future, I'm probably going to want to make that something that is defined in a configuration file. But for now, I'm just going to pick 20. And when you actually define this, you probably want to base the number of threads largely on your processor. So your processor has a number of cores, and each of those cores allows for a specific number of threads. And while you're not necessarily confined to that number, you can optimize the number of threads based on those numbers. So I'm not sure what the processor cores and threads are on this machine. I should, but I don't know it yet. So I'm just going to pick 20. It'll be arbitrary and things will be fine for now. So we've defined our thread pool. So now we can enter the infinite loop. So while one. And it's just going to continue accepting clients and passing them on to the thread pool to be handled. So we're going to accept a client. And here we want to go to the server, use the arrow to get the actual server embedded, and we want the socket. So that is our first argument. And then we need a struct sock ADDR of the server's address. So we're going to cast pointer the address of server dot address. And then finally, we need to pass in the length of this socket. So I'm actually going to define that up here for two reasons. One, it doesn't much like it when we call the size of function after casting. It doesn't really go well. Also, we only want to do it once. I don't want to have to cast this every single time. And I don't want to have to call the size of function every time. Here we are going to be casting it every single time. So, we might actually want to do that. So let's say sock or struct sock ADDR. This is just going to have a minor impact on the performance, but preventing it from casting this every single time it goes through this loop will make things a little faster. So we're going to call this sock addr. It's not very creative, but there we go, equals the address of server.address. And we should probably cast this, just to be specific there. Also, we're going to use an unsigned long to get the length of this address. Equals the size of server.address. I'm using an unsigned long here. Usually I was using integers as the result of size of, but size of returns an unsigned long. And what will happen is that you end up implicitly casting it as an integer. And while it's generally fine, it will usually work, you lose some precision there. And implicit casting isn't necessarily the best way to do things. So I find that to just use this unsigned long data type just prevents you from having to worry about that. So I've actually gone through the library and changed every time that size of is required, I've changed it to an unsigned long. But anyway, we're going to pass this address length. And instead of this, let's just pass in sock addr. Okay, so we have that. And now that we have accepted the connection, we want to pass that on to the thread pool and its work queue. And this is going to be a bit tricky. If we look at our thread pool, so the thread pool, let's see, where is it going to execute it? It executes this generic thread function every single time. And this generic thread function takes one argument, that is a void pointer. And so we need a single void pointer to handle this. So our handler function is what we're going to pass into the generic thread function. So the generic thread function is going to execute the handler function. And we need to do that with what is called the thread job. Where did I define that? Over here. So our thread job takes a single function that is going to be the function that we want executed. So in our case, the function that is associated with a specific route on the web page and any arguments that it needs. So we need the function that we pass into it to take a single argument and return a void pointer. So we have to sort of construct this carefully. So let's go ahead and come back to our HTTP server. And one thing I can see right off the bat is that I'm going to need two arguments in a function that can only take one argument. So the thing we're going to be passing off to the thread pool is the handler function that has to return a void pointer and accept a void pointer. And the handler is going to need to find the route associated with the request. So it needs the HTTP server and it needs the client. So we need a way to pass two arguments to a function that only accepts one. So what we're going to do is define a struct. Now, I don't want this struct to be part of the library per se. I'm not building this so that it can be implemented elsewhere. So I'm going to put it in this .c file to mimic what would be called a access modifier in C++. So this would be a private access modifier. It won't be accessible outside of this file. So struct client server. And we are going to add to it an int for the client. And we are going to put in a struct HTTP server pointer server. And what we want to do before we accept it is actually implement it. So we're going to have a struct client server, and we're going to do this as a pointer because since the handler function, that is the function that is going to be using this, exists outside of this while loop in a thread, we don't want to have to worry about the scope of this client server. It's going to go out of scope as soon as the loop is done executing that one iteration. So we actually want to use malloc to put it on the heap. That way we can destroy it ourselves later. And we'll call it client server. And we're just going to use malloc and the size of a struct client server. In previous videos, I've been actually casting the result of malloc, but here we can use an implicit casting to this client server pointer, and that actually works fine. I don't know if that is, specifically, I don't know what the difference is between casting this as an integer and this as a client server pointer. Maybe the fact that it is just a pointer makes the implicit conversion less of a problem, but I'm not really sure what the difference is there. Or maybe it has to do with the fact that casting an unsigned long to an integer, specifically that implicit cast, loses precision, whereas here it doesn't. I don't specifically know the difference there. If you can enlighten me on that in the comments, I'd appreciate it. But we're just going to use that casting here. So we have put our client server on the heap, and then we have accepted this. So we want to actually put that into the client server. So client server client equals the result of that. And that's going to put the address of the client into our constructor or our client server object. And then we want to say client server server equals server, the same HTTP server up here. That's going to give us access to all of the routes of the server. Now we need to insert this into the work queue of the thread pool. So we're going to need our handler function. So we're going to define a function that returns a void pointer. We're going to call it handler, and it's going to accept a void pointer called arg. Our argument is going to be this client server object. So we're going to say thread pool dot add work. And what does this take? Takes a thread pool, so a reference to the thread pool itself, and a thread job. So we actually need to create the thread job first. So struct thread job, and we'll call it job equals thread job constructor. And here we need to pass in the function. So this is going to be handler. And our argument is going to be this client server. So it's going to execute the handler with the client server as an argument in handler. So let's go ahead and define handler so this makes a little more sense. So void pointer handler, void pointer arg. What we'll do first is cast our argument back to a client server struct. So struct client server equals the dereferenced struct client server pointer casting of arg. Now, why do we want to do this? So we could remove this dereferencing symbol and make this a pointer, but then we're going to have to remember to free it later. And what we actually want is to free it immediately. That way we don't have to worry about it anymore. And so this is going to create a new client server object and just copy this one over into it. Then we're free to free this one, remove it from the heap, and we'll just be left with this one on the stack, which will automatically go out of scope as soon as the function is done. So we're going to now free arg. That way we don't have to worry about any memory leaks. Now what we need to do is actually execute this. So the client server is first going to read what the client is asking for. So we're going to create a request string. So a character pointer request string. And we're going to give it a size of 30,000. I'm probably not going to keep that as 30,000. I'll probably do it maybe whatever the size of 16 megabytes is. So 16 megabytes is the largest size thing you can send over HTTP. I don't think that is, having built this server, it seems more like that's a standard that has been decided upon rather than an actual limit on servers and HTTP, because HTTP is just a template. It's not a protocol, so to speak. It seems like servers just choose to reject things at 16 megabytes. I could be wrong about that, but we can just stick with the standard and put whatever the size of 16 megabytes is in there. But for now, let's just leave it at 30,000. And what we'll do is say read, and we're going to pass this the address of the client. So client server dot client, a void pointer to the request string, and the size of that request string, which is 30,000. So now we have our request string, and we can parse out this request string into an HTTP request from these protocols. So HTTP, struct HTTP request, we'll call this request equals request constructor, HTTP request constructor, and request string. Totally spelled that wrong. Okay, so that's going to create a series of dictionaries about this specific request. From that, we can actually get that request. So what we'll do is, or search those dictionaries for the route that we want. So we're going to define a character pointer called URI, and we're going to set that equal to request line dot search. And what do we want to pass into this? We're going to pass a reference to the dictionary, a void pointer, and the size of what we're searching for. So we're going to pass in the address of request line, and then we want to search for URI, and then we want to pass in the size of URI. Okay, so that is going to give us the actual URI, and then we can use that to search the server's dictionary of routes for the actual function that we want to execute. So this is where it gets a little tricky, so I'm going to do this one step at a time. Let's first define, what do we need to define first? If we look at our server.h, routes. We want to define a route object. So this is what the search from that dictionary is going to give us. So let's go ahead and define a route. So struct route, we'll just call it route. And we're going to set it equal to client server dot server. Now that's a pointer. So we want to search its routes dictionary, passing it the address of client server dot server routes, and then we want to search it for URI and the size of a character array with the number of elements that is the string length of URI. So that's another odd thing that I've been noticing, is that I can pass in a string literal to size of and get the correct answer, but if I pass in the actual variable URI here, I've been getting some strange results from that. So maybe one of you can explain what's going on there a bit more to me. And it doesn't like this anyway. So called object type struct dictionary is not a function or a function pointer. Because I need to say dot search. Okay, so that's going to not do anything yet. Okay, so let's define this as a pointer. And that should work fine. There we go. So our search function in the dictionary returns a void pointer to the data that's stored in a entry that is itself in a node. So That's why I'm getting a void pointer as the result here, and I just can implicitly cast that as a pointer to a route struct, and everything will work fine. Now we can actually get our route function, and we want to pass this off, or do we want to actually execute it? So yeah, we just want to execute it. So route to route function, and what does this take? Takes a reference to the server and the request itself. Route function, so we'll pass it the client server dot server. It's already a pointer there. And then we need the actual request. Now, do we need to worry about scope here? So we pass that off to this function. This function is being executed by the thread, but now that thread is just going to execute the function that this is calling. And so our client server or our request object is not going to go out of scope until this function finishes. So we can leave this as a local variable. Bit confusing. So what's going on? Let's contrast this with this while loop here. So over here, we create a client server instance, and then we pass that off to the thread, or we will pass that off to the thread in a moment. And once we have passed it off to the thread, the while loop continues to execute in the original thread. So this variable, if it wasn't a pointer defined by malloc, then it would go out of scope and stop existing. And it might be the case that when the thread pool gets around to executing that job, that variable will have gone out of scope and there will be nothing in there. So that's why we need this one on malloc. It's because this is going to start a thread. This one, the handler, is executed by a thread. And within that thread, these things aren't going to go out of scope because all of this has to execute before any of it goes out of scope. And this function is called. All of this will still be in scope. Once this function is done, then this function can finish, and then these things go out of scope. So it will still be available. So we can just pass this the actual request. And I'm forgetting if that needed a pointer, but I'm sure it'll yell at me if it does. Doesn't seem like it. Oh, maybe it does. Yep, it likes that. One good thing to think about when you use pointers in this sense is that it sort of is a little bit more efficient. So if you think about what happens, I create this HTTP request struct, and then I just pass its address into the function. So that function can go right to the address and see exactly what's written in there. If I passed a non-pointer, it would make a copy of request, and that would be executed in the function. But I would have to duplicate all of the thing that was in the original place, and that's going to take some processor time. So if you pass in pointers, things move a lot faster. Remember that here, this actually is a pointer because in our client server object, the server itself is already a pointer. Okay, so it's going to execute the function that is associated with that URI, and it is going to pass it the server and the request. And once that is done, what is going to happen? Well, the route function always returns a character array. So we're going to say character array or character pointer response equals route function. And then we are going to say write, and we're going to say to the client, so client server dot client. We're going to pass it response. And then we want size of a character array with the number of elements equal to the string length of response. Is that all good? What is it not like here? Interesting. So my HTTP request constructor doesn't like this request string. well, first of all, let's make it so this will actually compile. I'm going to come back to that one. So this one is going to return null because there's nothing to return. There's nothing even to catch it. And we are going to need to actually insert this into the thing, into the thread pool's work queue. And what is it not like here? We want address of address length. No. We need to cast it. Okay. So this takes a socklen t pointer, address length, that's good. And then the rest of these are unused variables. This one I'm going to need to take a look at. So let's leave that alone for the time being. Now, we know what this handler is going to do, and we have passed this job into the actual thread pool's work queue, or we have created a job to be passed into the work queue. So what we actually want to do is say thread pool dot add work, and this is going to take a reference to the thread pool itself and a thread job to be done. So add work, the address of thread pool, and job. And do we need to do the same thing here where we use malloc? I don't think so. So if I come back to my thread pool object and I look at add work, so what's going to happen is this function is going to have to execute before this function or that iteration of the loop. Where is it? Before this iteration of the loop can finish, this function has to finish, and job will not be out of scope. And what happens when we execute that function? Well, when we add the work, we are going to push this into the queue. And I happen to know, I could go through and show you, but just trust me on this, that the queue is going to automatically put this job on the heap for us. We don't need to worry about doing that. It's just going to do it for us. It can go out of scope, that local variable can stop existing, and that will be fine. I should delete that file because there's nothing in it. Anyway, so we have our infinite loop. We create a client server object. We accept a client, and then well, that seems unnecessary. Well, we have to do it. So we put the server into the client server, we put the client into the client server, we then create a thread job, and we pass that thread job into the work queue, and that's all we need to do in the launch sequence. Once it's in the work queue, we can go and start worrying about connecting or collecting our next client. So this is going to be much faster for the clients. All we have to do is take one, associate a job with them, put it in that queue, and then we can just take the next one and keep doing that. Over here in that queue, we'll have 20 threads, all taking things out of the queue and executing them one at a time. And what they'll be executing is actually the function that is defined with the URI in the routes of the server. So a lot of interesting things going on here. And the last thing I need to do is take a look at this. It doesn't like that it's a character pointer of size 30,000. All right, got it. So the problem was that when I created this request string, I was actually defining it as a pointer. So this is actually an array of 30,000 pointers, and those pointers would themselves point to characters. So what I actually needed to do is just define a character array of size 30,000 and then pass the address of that array in with its size to the read function. And there's a nuance here that is worth explaining. So arrays are pointers. So when you define an array, when I define this char request string array of size 30,000, what the variable request string actually holds is the memory address of the very first element. So let's make a simpler example. So if I do int x, and we define that as an array of size 3, x is actually a pointer to the first element in this array, that is index 0. And when I specify that I want x2, what it does is move that pointer 2 elements to the right of x. And since we know x is an int and an int has 4 bytes allocated to it, we just move that 8 bytes to the right, and now we have what element we're looking for. So an array is a pointer. So when I defined character pointer request string of size 30,000, I was actually defining an array of pointers, not the thing I thought I was trying to do. So by making this just a character array of request string size 30,000, this is already a pointer. So when I read it in, I can just read in the request string. And does that need to be an address of, since it's already a pointer? Will that work? That seems to work. So I can just read into it the request string. This is already a pointer, so we already get this. And then the size 30,000. Also, when oh yeah, there's one other thing. It's just this here. So I did the casting in this except function, and as we had already established, that would lose some efficiency. So I changed this so that I cast it up here outside of the while loop, so we can do it once and only once, and we never have to do it again. And that should be it for now. One other thing that I was thinking is that with this handler function, I could leave this as a pointer and not dereference that there. And let's go ahead and clear that. And what I will do, so this is actually just going to set this pointer equal to the same memory address here. And what we'll have to do is turn all of these into arrows. So those share the same pointer there, pointing to the exact same memory address. And now at the very end of the function, I can free client server, or I could free arg. Either one, it doesn't matter. It's just a pointer. It's the same pointer pointing to the same memory space. And the difference here is a mild improvement in performance. So when someone connects to the server and makes a request, rather than spending time copying this and then freeing it and then actually doing something with their request, we move right into doing something with their request, just copying over this address into a local variable so that it makes sense in the code. And that is a very small thing to do. And what you'll notice is that we write back to the client before we actually try to free that object. And the benefit here is that the client will get their response, and then we'll do that extra work of freeing the object. So the thread will continue working on something after the user has gotten their response. And from the perspective of the client, it's just going to seem a little bit faster. It has to do almost exactly the same thing, minus copying everything over, and you get a slightly faster response. Now, how much faster? Imperceptibly faster. You are not going to notice that I have done this. But if I don't do it, and I don't implement a philosophy of always trying to make things that little bit faster, those inefficiencies compound. And it will be a lot slower in the long run if I don't implement these tiny little improvements. So that was just something I noticed. I think that will do it for today. We've got everything ready and working in the launch sequence in Handler. And the next step is going to be a demo video of my application. So I'm going to create some HTML files and make a demo website for this. And I'll actually put the website up so that you can see it. The video associated with that is going to be a little bit different from usual. We're not going to be doing much coding in it. And I'm going to be expecting people who have not been following along with the series to be watching it. So I am not going to assume that you have seen all of this before. So if you are a regular on the channel, first of all, you're a hero. And second of all, it will seem a little bit, what's the word? Unusual. That's not the word I'm looking for. I'll put it in the description if I think of the actual word. Out of character, that's not really it either. Anyway, so it'll seem a little bit unusual. I'm going to be demoing the website and actually showing how I've built one to kind of demonstrate the functionality of this. And other than that, that will do it for today. You guys have seen YouTube videos before, so now I'm going to ask you to leave a like on the video, subscribe to the channel, and hit the bell so that you can get notifications when I upload. All is more helpful than it seems when YouTubers ask it. It really helps YouTube itself actually promote my videos and help me get the channel growing. So I really appreciate it when you guys do that, and especially your comments. I really like your comments too. So anyway, that'll do it for today, and I will see you next time. Toodaloo.